So, hello students, let us continue our finite element calculations. In the previous lectures, we have seen how to evaluate the stiffness matrix and then the load vector due to the body weight, the stresses, the surface pressures using the different isoparametric concepts. And now let us continue and see one very important aspect, that is the patch test, and then how we can use the finite element programs for doing the modeling. Okay. So, till now we have seen two types of elements, C0 and C1. The C0 elements, these are the elements where only the displacements are the field variables, and only the continuity of displacements is ensured at the interface between the elements. So, these are called as C0 because the first order derivatives may or may not be continuous, whereas the C1 elements, we have seen the C1 elements in the context of beam elements, where our degrees of freedom are the displacements and then the rotation, like dou w by dou x. Okay. And both the displacement and their first derivatives are the field variables, and the continuity of beam elements and their first derivatives are enforced at the inter-element boundaries. These are called as C1. And then C2 elements are where we have displacements, first derivatives and then the second derivatives, the rotations and then the curvatures as degrees of freedom, and these are with thin shell elements, but we do not come across them in the geotechnical engineering. We will be only seeing the C0 and the C1 type element. Then how do we get convergence? See, there are two methods. One is by H method and the other is by P method. H method is the size of the elements is decreased continuously to improve the accuracy. So, you start with let us say 100 elements in the mesh, next you increase it to 200 and then increase it to 300, 400 and so on, so that the size of the element goes on decreasing. Or in some cases what we do is we identify some critical point and then around that we can refine the mesh, make it more finer. Okay. And in this H method, we are not going to change the type of element. Like if you have a 4-node quadrilateral, we continue to use the 4-node quadrilateral everywhere. And there is another method called as the P method, where we try to get higher, more accurate results by increasing the order of elements. So, you might start with a 3-node triangle, you might increase it to 6-node triangle, or a 10-node triangle, 15-node, 21-node and so on, or with respect to quadrilaterals, like we may have 4-node quadrilaterals, 8-node, 9-node, 12-node, 16-node and so on. Okay. And this is the P method, where the size of the element may remain the same. Like let us say initially you have 100 elements, it will continue to have 100 elements, but we may have more number of nodes because we are increasing the order of the elements. And there is one test that is called as a patch test, that is performed numerically. So, we have seen the same test earlier in the context of our generalized coordinate method. So, we have seen that if you include the constant term, we can simulate the rigid body deformations without developing any strain. Then if you subject an element to constant strain state or constant stress state, we can predict the same thing within the element, and the same thing we are going to demonstrate numerically. And this particular one is done through the finite element programs, and this is to check the validity of an element formulation. And sometimes, see, the element may be correct, but we might have made some mistakes in the program, and by doing this we can verify whether the programming is also correct. and this procedure was first developed by Irons. In fact, Irons was the one who gave rise to lot of these finite elements like the isoparametric elements and so on. And the patch test also serves as a necessary and sufficient condition for correct convergence of finite element formulation. So, that is, if we are able to pass the patch test, that means that our elements can satisfy the monotonic convergence requirements. And sometimes a patch test, a mesh may not pass the patch test, but then as you make the mesh more and more finer, you might pass the patch test. That is also acceptable. And this particular example I have taken from the Cook's textbook. So, when we take a patch of element, it should be arbitrary patch of element, and then we subject it to some loading and some boundary conditions, so that they represent the constant pressure state. And here I have taken a patch that is 6 units long and 4 units height, and then on the right hand side there is a pressure sigma c applied. Okay, on the left hand side also there is the same pressure applied, and then this node 1 is fixed on a hinge that both x and y direction displacements are not allowed, and node 2 is on a roller. That is, the mesh can move vertically but not horizontally. Then all these elements, they are 4 node quadrilaterals and distorted. Only one element is a rectangular element, and all the others are distorted. And then we have the same pressure acting on this surface also, and we know that on any 2 node surface the load is distributed equally between the 2 nodes. Okay. So, here if our sigma c is the pressure applied, the force at each node is sigma c multiplied by this height multiplied by unit thickness divided by 2 is your force at any node. Okay. And so the sigma c times 2 divided by 2 is your F, and then same thing if you do for this element, that is you get an F. Then at this node you have an F from this element, and then you get another F from this element, so you have 2 F. Similarly, if you apply on this surface, you get 1.5 F and 1.5 F here. So, 1.5 F is applied in the negative direction, and here this is put on a roller, and then I think and see, and then there is some Poisson's ratio and then some Young's modulus given. Then we do this analysis, and if we calculate the same constant stress all through the mesh, that means that the elements are passing the patch test. And here, see, the boundary conditions also should enable the mesh to pass the patch test. So, here by placing this node on a roller, we are allowing for Poisson's ratio induced deformations. So, as you are elongating the mesh in one direction, the other direction the mesh should contract because of the Poisson's ratio. So, if you had placed this node on a hinge, then obviously this patch will not pass the patch test, because it tries to contract in the other direction, but then you are not allowing. So, it will develop some extraneous stresses. Okay. So, if you apply some stress, the stress that is predicted here in the inside the elements should be the same. Okay, that is what we are going to ensure from finite element analysis. And in this test, we are going to load the boundary nodes consistently derived from our n transpose T ds calculations, and then the internal nodes are neither loaded or restrained, and the patch needs to be provided with just enough boundary support to prevent any rigid body deformation. And so that is what we have done here. So if you fix only one node and leave all the other nodes, then it can undergo the rotation without any limit. So we need to constrain one more node, and that we have done by constraining this, and you prevent the rigid body deformation, and then we should be able to predict this constant stress that we will see through a program. And so sometimes the elements may not pass the patch test, but as you make the mesh more and more finer, you might be able to pass the patch test, and that we call as the weak patch test. And the constant stress should be there in all the quantities, sigma xx, sigma yy, sigma zz, tau xy, and so on. Then if you have bending element like a beam element, even the moment should be constant all along the length. I think and we have already seen that sigma of ni should be equal to 1 for monotonic convergence, and usually all the elements that we have, they do pass this this patch test, because all the elements, isoparametric elements that we have derived, they have this condition of sigma of ni is 1. Okay. And we can actually do a combination of different type of elements, like 4 node, 5 node, 6 node, and so on. That I will demonstrate when we go into the finite element program. And there are different types of finite elements. Say the 4 node quadrilateral is what we have seen, and then the 3 node triangle also we have seen in our calculations. And we can divide this 4 node quadrilateral into 2 triangles like this or like this, and these elements are too simplistic, and they are good only for problems where the stress is absolutely constant all through the mesh. For those cases, we may be able to get reasonable results, but otherwise we should not use them, or we should refine the mesh so much that we can approximate the stress field that we get. And within geotechnical engineering, the experience is that if you divide any rectangle into 4 triangles like this, we can get good results for plane strain problems, for a strip footing or an embankment or something, not for axisymmetric cases. And the rectangles divided into 4 3-node triangles give a very good result, comparable to an 8-node quadrilateral element for plane strain. But for axisymmetric elements, for axisymmetric problems, we need to go in for 8-node quadrilaterals or 6-node quadrilaterals or 6-node triangles, or even higher, like 10-node triangles or 15-node triangles, and so on. Okay. And how we decide whether a given element is sufficient for a problem or not, we can guess it by looking at the variation of strain within the element and see whether that can represent reality. So let us do that for a 3-node triangle and 4-node quadrilateral. So in a 3-node triangle, our displacement field can be written as A0 plus A1x plus A2y, and our strains epsilon xx epsilon yy and gamma xy, we see that they are all absolute constants. So the 3-node triangle per se is a constant strain triangle, and so when you apply it, we should be careful, because if you use a very large element, then within that large area you are assuming that the strain and stress are going to remain constant. So that means that you are unnecessarily constraining a lot on the system, and your result may not be accurate. And when we go into the 4-node quadrilateral, our displacement field is A0 plus A1x plus A2y plus A3xy, and our epsilon x is A0 plus A3y, and epsilon y is A2 plus A3x, and gamma xy is A1 plus A2 plus A3x plus A3y. Okay. And so here we see epsilon x is a constant along x direction but varying along y direction, and epsilon y is constant along y direction but varying along the x direction, and gamma xy can vary both in x and y directions. So when you apply this, we should be careful, because the 4-node quadrilateral is also directionally constraining the variation of the strain. And so if you let's say if you use a 3-node triangle for analysis of a cantilever beam, we'll have a problem, because 3-node triangle assumes that the stress is constant and the strain is constant. So that means that within a cantilever, we know that on the upper fiber we will have tensile strain, whereas bottom fiber will have compression strain. But then if you represent with a 3-node triangle, it will either give you compression or tension. So that's not correct. But then if you apply a 4-node quadrilateral, the epsilon x, that is the flexural strain, is a function of y. So it has a capacity to represent tensile strain at the top and compression strain at the bottom. So that way the 4-node quadrilateral may be better compared to a 3-node triangle. And then even more versatile than these are higher order elements like 8-node quadrilaterals or 6-node triangles and so on, and by using them we can get better result. And when we choose the number of terms, we have to carefully examine the Pascal triangle in choosing the terms, and this particular one is given in terms of Cartesian coordinates x and y, but you can write the same thing in terms of natural coordinates xi and eta. And all our Lagrange elements, they include only the terms within this highlighted areas, and the Lagrange elements, they include some higher order terms, but while neglecting some lower order terms. Okay. Like for example, the 16-node Lagrange element, it will have this x cube y cube term, but then it will not have this x to the power 4, y to the power 4 and so on, all these lower order terms. Okay. And say sometimes we may get some spurious results, and that you might think that's because of the programming errors, but that is not true. In some situations, depending on the constraints that we have, we may get some result like this. So here this yellow mesh is showing the rigid footing resting on a soft clay, and it is subjected to some concentrated load, and we know that it's a rigid footing resting on a soft clay, and if you subject it to some loading, it should just simply sink into the clay. But then the response that we get is very funny. See, this particular one, it's a rigid element with a very high modulus, but then it has buckled something like this, it has twisted out of shape, and whereas even these elements, they have distorted a little bit different. And the main concern is, see, our rigid element with a very high stiffness, it is just buckled out of shape, or it has got twisted out of shape. That's because of insufficient restraint given by the soft clay, and this particular result is obtained with 2/2 integration, numerical integration. For all the elements, the stiffness is evaluated using 2/2 numerical integration, and the same thing performed with a 3/3 integration is giving the result that we expect. So, if you have a rigid element, it should just simply move like a rigid body. It should undergo a uniform settlement all through, whereas here it has not done. It has undergone some settlement outside, but then inside it has not undergone equal settlement. And you might think maybe this mode of deformation is excited because of this concentrated load. Actually, in the plane strain, there is nothing like a concentrated load. It's a line load. That is because the concentrated load can happen only in a full 3-dimensional problem, but not in the 2D problems. So, even if you apply pressure loading like this, we get the same spurious response because of insufficient restraint provided by the soft elements. And I am going to show one more example on the cantilever beam subjected to tip load and moment, and because this is a problem that we understand very well, and if we have a pure flexural member without any shear deformation, these are the deformation and the rotations. Delta is PL by 3I, theta is PL square by 2EI, and delta is ML square by 2EI, and theta is ML by EI. These are the results that we should expect with pure flexural elements. And but then if you use a plane stress element for representing a cantilever beam, that being a continuum, it might undergo some shear deformation, and the shear deformation at the tip is 6 PL by 5 AG, where G is the shear modulus, A is the cross sectional area, P is the applied load, and L is the length of the beam. Okay, and these are for different properties. Let's say the length is 10 and the depth is 2, and the Young's modulus is so much. The load is at the tip is 100, at the moment is 100, and the deformation at the tip is 2.5 times 10 to the power of minus 4, and the rotation at the tip is this, and the deformation due to the moment is this, and rotation due to moment, applied moment is this, and we can perform these the finite element calculations and see what happens. Okay? And actually there are two different geometries considered for a 4-node element mesh. These are the geometric parameters, length is 10 and d is 2, and for 8 and 9 node elements the length is 100 and the depth is 10. Okay? And this Cook's textbook, he has shown the result qualitatively, what you get with the different type of elements, and this is for a cantilever beam modeled by using the one single 4-node element, and the deflection at the tip is only 9% of the actual deflection, and then the stress at this point, at the bottom fiber at the bottom, is only about 10% of the actual flexural stress. But then if you have more number of elements like this, your deflection is slightly better. It's 68% of the actual result, and the stress at this point is about 73% of the actual stress. But then if you have the same 5 elements but distort them like this, your solution accuracy comes down. The tip deflection is only 0.49 times the actual deflection, and then sigma c at this point is only 30% of the actual stress. And if you use 8 and 9 node quadrilaterals, and 3 different cases are given, one with pure rectangular elements, 2 of them, and one with the distorted, but then this surface is a straight surface. Then the third one is distorted, but it's a curved surface. And for this case, with the 2/2 integration, if you use 8 node element, the sigma at this place is exact 1 times the actual stress, so that is 100% exact, and the tip displacement is not bad, 0.968 times the actual displacement. But then if you use a 3/3 integration, the calculated stress is much more than what it is, like it's 1.129, and then the deflection is slightly lesser, 0.93 times the actual displacement. And if you use a 9 node element with reduced integration, you get very good result, both in terms of the stresses and then the deflections. And 9 node element with the 3/3 integration, it's not very good. And when you distort it, your results suffer a lot. See, with the 2/2 integration with 8 node element, your vertical displacement is 0.36, but then if you use a 3/3 integration, your solution is only 0.16 times. So that's actually, that is so you see, as you are increasing the order of integration, instead of improving the solution, you are actually impairing the solution. It is, the accuracy is coming down consistently in both 9 node and 8 node elements. Okay. Then this is a curved element with a curve, and once again this 8 node element, it's not able to perform well, whereas the 9 node element with the 2/2 integration, it is able to reasonably predict. The deflection is 95% of the actual deflection, and the stress is about the same 95% of the actual deflection. So this I will show through a computer program, and so our continuum elements, we have only facility to apply the forces either in the x direction or y direction, but then how do we apply a couple or moment? So what we do is we can actually apply the force like a couple. So if you want to apply a moment of m here, we can equate m to PD. If d is the depth, we can calculate the load that you need to apply, P, and apply in the positive x direction at the top and the negative x direction at the bottom to get our moment. Okay. So similarly, if you want to get flexural stress, so when you have a beam, the flexural stress we get directly, and then but then our sigma x is actually m by I times y bar. M is the moment, that is the shear force multiplied by the distance, okay, and the at the fixed end your moment is p times L, that's maximum at the fixed end and 0 at this the free end, and at any place you can calculate the moment m by I and compare this flexural stress against this sigma xx, and that is what is reported here, the percentage error or the how it compares with the actual result. Okay. See, till now we were only discussing about the quadrilateral elements, and I want to just briefly show you about the triangular finite elements. And the triangles are also very popular. And as you know, the triangular elements they have the complete polynomials starting from 3-node triangles, 6-node and so on, and so their stability is better. Some of the modes of deformation that you see with quadrilaterals may not happen with the triangular elements. Okay. So our and there is another method for getting the shape functions, that is in terms of the area coordinates, and here we can define any node P and then get the area of any of these smaller triangles like P23, P13, P12 and so on, and the N1 can be written as area of this P23 divided by the total area. Okay. And so that when P is located at node 1, N1 is 1, and when P is located at 2 it is 0, or when P is located at 3 it is 0, and then in between it varies from 0 to 1. Okay. And this definition of finding the shape functions in terms of the area of these triangles, it will give us the same shape functions that we got earlier, that n is a plus bx plus cy by 2 delta. That is what we derived earlier by using the generalized coordinate method. We will get exactly the same things. Okay. And it is possible to develop shape functions for triangles using our isoparametric procedures, and the xi and eta for the triangles they vary from 0 to 1, not from -1 to +1, and xi and eta are not orthogonal in this case, whereas in the case of quadrilaterals we have taken them as orthogonal, but here it is not so, and so they do not vary independent of each other. So each sampling point will have unique xi and eta values. Okay. And we can define say xi along the surface 1 2 and eta along this line 1 3, and let us say that xi and eta are 0 at this node 1, xi is 1 here and eta is 1 there. Okay. And the xi along this line is 0 and along this line is 1, is parallel to this surface, and then eta is 0 along this line and then 1 along this line, and in between it is varying from 0 to 1. Okay. And we can get our shape functions in terms of the natural coordinates xi and eta using our conventional generalized coordinate method. So our u can be assumed as a0 plus a1 xi plus a2 eta, and then when we go through the procedure and derive, we will see that n1 is 1 minus xi minus eta, n2 is xi, n3 is eta, and our n1 plus n2 plus n3 is 1 because it is 1 minus xi minus 1 plus xi plus eta. And we can get our shape functions for higher order elements by going through our generalized coordinate method. For the 6-node triangles, the u is a0 plus a1 xi plus a2 eta plus a3 xi square plus a4 eta square plus a5 xi eta. This we can easily get by looking at the Pascal triangle, and if we go through them and substitute different xi eta values here and then determine the a0, a1, a2 and so on, we get the shape functions like this: n1, n2, n3, n4, n5, n6. And so whatever progressive corrections that we had done with quadrilateral elements can also be done with triangular elements. So the n1 for the 6 node element we can get from by correcting the n1 from the 3 node element n1 3, we can get it, we can subtract n4 by 2 and n6 by 2 and get the shape function for a 6 node element. So our n1, n2, n3 they are given here for the 3 node element, and for the 6 node element we can get this, and in between we can have a 4 node triangle or 5 node triangle or a 6 node triangle. It does not matter, because whatever procedures that we discussed earlier are also valid for this particular element. Okay. And these are the sampling points for the triangles, and one point integration, this is good for first order polynomial. The xi and eta are 1/3, 1/3, and the weight factor is 1, and we can have a 4-point integration that is good up to third order polynomial. Xi and eta are here, and the weight factors, and you see one of the weight factors is negative for the triangles. For the 4-point integration it is it's negative -27 by 48, then 25 by 48 at all the other nodes. Then 7-point integration, it is good up to 5th order polynomial. These are the different locations and then the weight factors, and the sum total of all the weight factors for the triangles is equal to 1. And our equations for triangular elements are written like this, and the determinant of the triangular elements of the determinant of the Jacobian matrix for triangular elements is 2 times the area, 2a. Okay. Whereas for quadrilaterals the determinant is a by 4. Okay. And so our stiffness matrix is written like this: B transpose dB Wi, because now we are not independently doing in xi and eta directions. We are at each and every sampling point we can have a different xi and eta values. So for say 1-point integration, xi and eta are just 1/3, 1/3, Wi is 1, and so on. Okay. And if you have more points, you have this the xi and eta like this, varying like this: 1/3, 1/3, 0.6, 0.2, 0.2, 0.6, 0.2, 0.2, something like this. I think it's illustrated here. And the load vector due to initial stresses and the load vector because of the body weight, they are all given here. And what are the best locations to find the stresses? See, till now we were looking at only the displacements, and the displacements are obviously determined at the node points. And so when it comes to the stresses, we have to see exactly where we are enforcing the compatibility conditions. So in the compatibility conditions are enforced at only the sampling points, the Gauss quadrature points, and so the strains are evaluated at these Gauss quadrature points, and then the stresses are also best evaluated at Gauss quadrature points or the Gauss sampling points. When we determine the stresses at the nodal points, they may or may not be correct. Okay. And in the nonlinear analysis, we always calculate the stresses only at the integration point, so that we can apply B transpose sigma and equate the internal force to the external force. and in general the order of error in the stresses is more than that of the displacements. So, if your displacement prediction has a 5% error, the error in the stresses need not be exactly equal to 5%, it could be more or much more sometimes. Okay, now let us see how we can simulate a thick cylinder subjected to internal pressure like this. So, we can and the dimensions, internal radius is 100 and external radius is 200, and we can do the analysis in two ways. One is in like a plane strain, and the other could be like an axisymmetric, and depending on how you take the cross section. And if you take a cross section like this along the length, you take unit slice, we can get we can model it as a plane strain case, assuming that in the length direction the strain is 0. Or you can take a longitudinal section like this, and then do this problem as a axisymmetric analysis. So, here actually we can take along the length direction, and then when you see this section, you will see only the thickness, and thickness that is rotated around the central point will give you the cylinder. Okay. So, that is what we do here, and so this is the mesh for doing the analysis of thick cylinder subjected to internal pressure. What we do is we take a unit length and support all these the nodes and rollers, so that the mesh can deform only radially, and that is the ideal case. If you have a very long cylinder and take some length in the mid section, you will have predominantly radial displacements, and that is what we get with this mesh. The other mesh, possibilities using plane strain model. So, if you consider a unit slice, this plane, we will get a thick cylinder like this, and it is not necessary to solve the entire thing. You can draw two symmetry lines, two symmetry planes here and here, and then whatever is happening in this positive quadrant, the same thing is going to happen in the negative quadrant, and so on. Okay. So, this is your deformed mesh, and the black one is the original mesh, and then the yellow one is the deformed mesh. And just ignore, because in this program it cannot draw curved surfaces. So, it is just drawn with straight lines like this, but it is a curved surface. Then it can also not plot the pressure loading correctly. Okay. So, that is a brief introduction to patch test and some aspects of finite element analysis. And if you have any questions, please write an email to profkrg@gmail.com. And before I wind up the class, just want to show you one program that you can utilize for doing all these isoparametric calculations. So, you are going to get one program called IsoCalc, and this is a very simple program, and it can do the calculations for quadrilateral elements, triangular elements, and then the traction calculations. And then you can do two types of calculations, the body force vector, or the force vector due to the initial stresses. And then you can do calculations for plane stress, plane strain, or axisymmetric. And then for different orders of integration, order of integration 1, 2, 3 and 4, up to fourth order of numerical integration you can do, and for the plane stress case you need to define some thickness, okay, and then we need to define the coordinates, and so here for each node we need to give x and y coordinates, and then this input box is common for both the traction and also for quadrilateral and then for triangles. So let's see, so if you choose the quadrilateral, automatically you get option for giving the coordinates for 4 nodes, because that's the minimum 4 nodes you need to define. Or if you choose a triangle, you get only 6 nodes like quadrilateral. Let me go back to quadrilateral. See, these quadrilateral elements are defined with variable numbers, like minimum 4 nodes up to maximum 9 nodes, and you may or may not involve the other higher order nodes, okay. So you can uncheck these boxes so that you will use only the 4 nodes, okay. And let's do some calculations. Let's give some numbers. Let's say our node 1 is at 10 and 10, okay, and at node 2 x is 0 and y is 10, okay, and node 3 is at the origin 0 and 0, let's say, and node 4 is at x of 10 and y of 0, okay, and let's say that we have you have a plane strain case and the thickness is automatically 1, and our order of integration we can select, let's say we select 2, and then let's say we calculate the body force vector. So the unit weight I am taking as 20, and the gravity factors 0 and -1, okay, and then you press this calculate, then it will do the calculation, and then it is showing -500 at all these 4 nodes, and your positive coordinates are like this, x and y, okay. And so now let's see, let me just choose axis symmetric, okay, and let us calculate the results with 1 point integration. The body force vector you calculate, and so with single point integration the axis symmetric element is given -2500 at all these 4 nodes, which is not correct because our shape functions, they have first order variation, and then our radius also has a first order variation. So you have totally second order variation, and then you need minimum 2 integration points. So let's try with the 2 integration points for this axis symmetric element. So I have a 2-point integration, and if you do the calculation we will see that it is different. The distribution has changed completely, -33 at the outer nodes, then -1666 at the inner nodes, okay. So it is then now let me demonstrate for an 8 node quadrilateral. I am choosing all the 8 nodes, and then our node 5 is at the top surface at x of 5 and y of 10, and then node 6 is at x of 0 and y of 5, and node 7 x of 5 and y of 0, okay, and node 8 is at 10 and 5, okay. And let's choose our plane strain case, okay, and let's see, let's try with the 1-point integration, and we have an 8-node quadrilateral N transpose B with single point integration. So if you do this, you see at the 4 corner points you have a force of 500, whereas at the mid side nodes you have 1000, 1000, 1000. So obviously this we do not know whether it is right or wrong, but you know from our previous calculations that the mid side node should attract 4 times the load at the corner nodes, but here we have only 2 times. So our order of integration may not be sufficient, so we can go back and change the order of integration to 2, and let's do the calculation. And here we get see plus 166 at the 4 corner nodes, whereas minus 666 at the mid side nodes. It is it's going down at the 4 mid side nodes, whereas at the corner nodes it is going up. That is what we had seen earlier. And now let me define the 9th node at 5 and 5, okay, and let's do the calculation. And now it has the nature of distribution has changed completely. It is at the middle, it is attracting the maximum force of 888, whereas at the 4 corner nodes is only 55.55. Okay. So actually these and let me do the calculation for this initial stresses. Let me just take a simple case at one integration point, okay, and let's say our stresses are sigma x is minus 50, sigma y is minus 100, and then shear stress is 0. Okay. Then if you do the calculation, you will get the forces. Interestingly, there is no force distributed at the 4 corner nodes, because I have used only 1-point integration, and it is it's not able to give us the correct distribution at minus 1000, 500, 1000, minus 500, and we can actually do a 2/2 integration and then see what happens. Let's give the same minus 50, minus 100, 0, 0, 0. So we are assuming that the element is subjected to some constant stress state, so we are using the same constant stresses. So if you do the calculation, now we get different result. See, we are getting forces at all the 4 corner nodes and also at the mid side nodes. Okay. Then after you do the analysis, you can save the results by doing this the report generator. So I am giving results.out, and if you press this report generator, the results will be saved in this file, and then we can open that file and then look at the results. Not sure exactly where that is saved. Yeah, here. Okay, these are the results that we get. Let me blow it up. Zoom. Okay, so we have eight nodes corresponding x and y coordinates, and then we have used a 2-point integration and the stresses are the same at all the points, and then the force in the x and y direction at each of these nodes. So, this is what we say as a consistent distribution of the loads, and that is what we need, so that our stiffness and the forces are consistent with each other. Okay. So, that is a brief introduction to this program, and in the next class I will demonstrate for more number of cases. Then we will also see the patch test, because that will take some time, and in the meantime, if you have any questions, please feel free to send an email to this to my Gmail address, then I will respond back. So, thank you very much. We will meet next time.